Hi class, we are now on 12.2 acid-base equilibrium reactions. So strong acids completely ionize in water. There are only 7 common strong acids that are listed here. We have hydrochloric acid, hydrobromic acid, hydroiodic acid. If you notice, those are halogens, 3 halogens. Nitric acid, sulfuric acid, perchloric acid, and chloric acid. These are the 7 that we consider strong. They completely dissociate into ions fully. Most acids only partially ionize in water. Those are weak acids. For example, hydrofluoric acid, HF, as you can see right here, is a weak acid. In solution, only about 2% of HF breaks into ions. The remaining 98% remains intact as HF exactly, and not as ions. The ionization of weak acids is an example of an equilibrium reaction. This type of reaction occurs in both the forward and backward directions. Hydrofluoric acid can ionize to form hydronium ions and fluoride ion, but the ions can also combine to reform HF. In order to show this, we use an equilibrium arrow, which goes it's like a half arrow one direction, half arrow in the other direction, which shows the reaction going in both directions. We're going to cover more detail in chapter 13, which is not true. I just didn't mean to read that sentence. We're not covering 13. We're jumping right to 14. That is our last chapter that we're going to cover here. So there are weak acids, and there's a number of weak acids, and they all partially ionize dependent on the acid. So not all of them do exactly this, where they stay at 98% and 2%. Some are more, some are less. I believe this is actually the less. But what it is that this will disassociate this way, and then some will come back together. The hydrogen and the fluorine will come into contact, and it'll go back this way. Why is it in equilibrium? Because there's a rate that this is happening for. So if you can try to imagine that for every one that goes this way, there's one that goes this way, or 2 that goes this way and 1 goes this way. There's a rate, and it's a ratio, and it matches, and that's what the equilibrium is that it goes one way, it goes the other, and the rate doesn't change. The speed of, think of people walking one way and other people walking the other. It stays constant. It's a consistent thing. So that's what this means. And so if this is in solution, it mostly stays as this, but there's a few ions that disassociate. But as they come this way, there's also some that go this way. So that's what equilibrium means. For strong acids, you don't get this. It'll be an arrow going one direction only, which is what we've been dealing with in reactions. But when you see equilibrium, that means that there's a back and forth going on. So let's consider the forward and backward reactions of this equilibrium in more detail. Going from left to right, the HF donates the proton. So you can see these electrons stay with the fluorine, and this hydrogen, the water, takes the proton away to the water molecule. This means that HF is the acid and water is the base. What about the reverse reaction? So if we're looking on this side, going from right to left, the hydronium ion gives the water back to the fluoride ion. In the reverse reaction, the hydronium is the acid and the fluoride is the base. When describing an acid-base equilibrium, we refer to the acid and base on the right-hand side of the chemical equation as the conjugate acid and the conjugate base. So you see this is the base, and then if we go on this side, we follow, it's now the conjugate acid. Because if we're looking at it going this way, because it's going to donate the proton back to the fluorine, which is what you see here. So that means that this is the conjugate base. So it's the opposite. So let's look at another example. Trichloroacetic acid is a weak acid. In water, this acid ionizes as shown here. In the following direction, the trichloroacetic acid donates the proton. It is the acid. In the reverse direction, the acetate ion is the conjugate base. Similarly, the water is the base in the forward direction, but the hydronium ion is the acid in the reverse direction. So, excuse me. This isn't, the trichloro, I'm trying to remember how to say this correctly, but, okay, trichloroacetate ion. There we go. Have to think about that for a moment. Notice that the only difference between the acid and the conjugate base is the proton. The acid form has the proton and the base does not. Excuse me. Because of this, we refer to the acid and conjugate base as the acid-base pair. The base and the conjugate acid are also a pair. The only difference between them is the proton again. So we match them up. Basically, you match up the pair. So on this side, you figure out what the acid is, and then you can figure out the conjugate base. And here where the base is now the conjugate acid, because we're looking at it going this way, but we can also look at it going that way. This is an important idea. So let's look at a different image. Imagine a dog and cat passing a proton back and forth, like an acid equilibrium. In the forward reaction, the dog is the acid. Can you identify the conjugate base dog? So if this is, it's the dog, so it's still the dog if you're going on this side, but it's without the proton. So that's what you're looking at, is you look for this one, but you look for it without the proton. This one doesn't have the proton, so this one means that this must have the proton. So you're still matching them up. They have to be identical in somewhat, think about the foundational compound. You can't just automatically say that this is the acid and now this is the base, because that's not true. They have to match up in the way they look. Hopefully that's making sense of the foundational compound. Many drug molecules, both legal and illegal, can undergo acid-base reactions. For example, drug producers commonly ship cocaine in the acid form, called the acid salt or the powder form. In the 1980s, drug dealers began treating acid cocaine with base. This acid-base reaction converts cocaine to the conjugate base, also called the free base form. By the way, I've never read anything about this before, so this is interesting. Commonly known as crack. So let me read that again. The acid-base reaction converts cocaine to the conjugate base, also called free base form, commonly known as crack. So in the powdered form, it's acid, but in the conjugate base, it's known as crack, and that's the base. That's interesting to me. It was not a new trick. For years, cigarette companies have treated tobacco with ammonia. Since ammonia is basic, it converts nicotine from its acid form to its conjugate form. This practice increases nicotine intake when smoking, fueling addiction and increasing the consumption of cigarettes. Notice that for each molecule, the difference between the acid salt and the free base is only the presence of a proton and a counter ion. Identifying acid-base pairs is an important skill. So let's look at one more example. Identify the acid-base pairs in the following equilibrium. I don't know if I pointed out here, but that's what they're talking about. The only difference here is that there's a proton and then a counter ion, which is close to the proton. So you see that's what's missing in this portion here. You can see that's what's missing in this portion here for nicotine. Okay, so let me go on. Identifying acid-base pairs is an important skill. So let's look at one more example. Identify the acid-base pairs in the following equilibrium reaction. The key to identifying acid-base pairs is to realize they are the same species, with or without a proton. So in the forward reaction, we notice that HBr donates a proton, leaving the bromide alone. Bromide ions, excuse me. Therefore, HBr is the acid, and the bromide ion is the conjugate base. By looking at, here we have, what is this? I have to look at it for a second. Okay, so now we're looking at methanol, and therefore, so if we look at this is the base. So by looking, its conjugate acid is the same species, as we can see over here, with an extra proton attached. So therefore, this is a conjugate acid and base pair. Okay, so let's look at one more. Look at the reaction of HF with water. In this equilibrium, we say that HF is the acid and fluoride ion is the conjugate base. Does this mean that fluoride ion is basic? Actually, yes. In aqueous solution, fluoride ions act as a weak base, removing protons from the water to produce hydroxide. And in this equation, we write the fluoride ion on the left-hand side, so we see it here. So it is the base, and HF is the conjugate acid. So this is what we're normally focusing on. They're just showing you in this what is happening with the base as well. But don't get confused and complicated. Focus on this one. This is the main one we want to look at. They're just showing you what fluorine's also, the fluorine ion is also doing, but they're not saying to what extent. And this is a weak acid here. So we're focusing more on the weak acid than the base part. So I'm going to tell you, focus on this one. Don't overanalyze this one. Yes, this is going on, but this is the main one that we're focusing on. Okay, so let's look at another one, our last one for the lecture. Hypochlorous acid is a weak acid. So this means its conjugate, which is the ClO minus, is basic. We can write two reactions showing how both the acid and the conjugate base react with water. So again, yes, they want you to know that these are both happening. I would strongly suggest you learn one first, and then once you're comfortable understanding this, then start looking at this. You should know them, but in order to really understand what's happening, you need to focus on one first before the other, is what I'm trying to say, and I think I'm doing it poorly. Okay, so we could show the acidic reaction, which is the top one. And we see that we have hypochlorous acid in combination with water. It produces hydronium ion and the anion to it. This is an equilibrium, so we see this is going this way, but it's also going that way. So, or we can show the basic reaction. So we take the base, and we put it here, the conjugate base, but we now make it just the base. And in the presence of water, it's also now producing, we can see that water donates a proton, and it ends up making a conjugate acid with hydroxide ions also being produced. So as a general rule, the conjugates of weak acids are basic. Sorry, I'm getting bases and basic and acids all mushed together here. The conjugates of weak acids are basic, and the conjugates of weak bases are acidic. There we go. I'm trying to talk faster than I should here. So let me repeat that. As a general rule, the conjugates of weak acids are basic, and the conjugates of weak bases are acidic. There we go. I said it. Now, let's take a look. So that's why these words are kind of confusing. But the good thing about these conjugate acids and bases is that they don't really change. If you can look at for the other species, you can see what's actually happening. And there's nothing really, difficult about it. Yes, it's difficult to learn in the beginning, but the patterns don't ever change. This is what's happening over and over with all of these, with weak acids and weak bases. That's what I'm trying to say. They don't get any more complicated than what you're seeing, which is nice. Okay, so let's take a look here. Acid-base equilibrium reactions. So here are the 7 strong acids. You should definitely know these. Remember I gave you guys that printout? You should be using that to write additional information when you use these for your exams and quizzes. You should definitely have something, if this isn't listed on there, which right now at the moment I can't remember, you should have this written on there. So you can refer to these, because these are treated differently than weak acids. They respond differently. When we're dealing with conjugate acids and conjugate bases, that is only for weak acids and weak bases. They do not apply to strong acids and strong bases. So you should definitely know these, get familiar with them. They will haunt you for all of your chemistry education. So equilibrium, when you see these equilibrium, this always means it's going back and forth at a specific constant rate. It doesn't ever stop unless there's a disruption to it. Acid-base pairs. So we can see, once you see one, you can find the other. They have to have the same species. So you can't say this is an acid and this is a base. They don't have the same foundational compound. They have to have the same foundational compound. So same as this. The dog and the dog go together. The cat and the cat go together. The difference is where is the proton. So let's label the acid, the base, the conjugate acid, and the conjugate base in these. So the first thing you want to do is look where on here. So follow this. This is HCl. This is Cl. So here, let's look at the top one first. We have water and we have HF. So we can see that HF loses the proton and it goes into the water. So in this case, we can see that this is the acid, this is the conjugate base. So if this is the conjugate base, this must be the conjugate acid, which means this is the base. So hopefully you guys are understanding. They have to partner up. You can never just make two conjugate acids and no bases. There has to be a partner with them or something's not right. I actually don't like this reaction, and I would have removed it, but maybe it's in your homework. I don't like this because HCl is a strong acid. It completely dissociates. And what they're saying is that it comes back together, which maybe it does, but I have never been taught that. So I actually don't like this one, but this is what they gave us. Since this is a strong acid, they don't usually use these in these reactions because HCl and HCl don't come back together. And if they do, somebody needs to tell me. But they have it here, so we're going to go and pretend that it does. So in this case, we have, we can figure out that this is acid, so this is the conjugate base, the base. So in this case, so here's the acid, here's the conjugate base. So in that case, that means that if that's the conjugate base, this has to be the conjugate acid, this has to be the base. And that's what happens, is it's taking it on. I will say in chemistry, they do add reactions and they do talk about things that don't work, but they don't tell you they don't work. So that's what I think is happening here, is they've created a reaction that if it does work, I'm surprised. Yeah, they teach you a lot of stuff that you find out if you actually go into chemistry and work in a lab. They don't work. What image best describes aqueous solution of HNO3? So the first thing you need to ask yourself, is this a weak acid or is this a strong acid? That is going to determine which one you pick here. So let's go back to the list. And it's right there, nitric acid, which means that 100% ionizes, or it's close to 100%, which means that most of the molecules, if not all of them, because that's what a strong acid means, completely dissociate and do not come back together. So if you take a look here, we see nitrate ions, nitrate. I don't see any that look like HNO3, where we see here HNO3, so B wouldn't work. And here we only have hydroxides and hydroniums. That's not true. And here we've got oxygen, which is not part of our equation. So this is going to be A. It completely disassociates. When you get these, that's the thing you have to ask. Is it a strong acid or a weak acid? Is it a strong base or a weak base? And that's going to tell you what the behavior is, what happens in solution. Ammonia is a weak base. So it's telling you right there it's a weak base. Weak base means it's going to mostly stay fully intact with very few that ionize. So which is the best image here? I'm just going to jump down and cheat. And it's going to tell you B, and that makes sense. Because remember, this is not producing, it's not losing any hydrogens. What it does is it reacts with water and ends up removing a proton. So the proton goes to producing hydronium ions, and it produces hydroxide from the water. We've covered this in the last section. So if you're not familiar with that reaction, go back to that section and you'll see the balanced equation. In the following reaction, water acts as a, let's follow it. Here we have HCN. So let's see what happens. We can have CN minus here. So that means that this is acid. This has to be the base. So it is a Bronsted-Lowry base because it is a proton acceptor. Ammonia is a weak base. What is the conjugate acid of ammonia? Well, if it's a base, that means it has to take a proton. So we've got to look for something that adds a hydrogen on it. So here it is. It would be E. Acetic acid is a weak acid. What species has the highest concentration in an acetic acid solution? So this one would be interesting because if it's a weak acid, it stays mostly intact. So we're not going to have a high concentration of protons. We're not going to have a high concentration of the acetate ion. What we are going to have is mostly intact. So it's going to be the acetic acid staying together. Which solution has the highest concentration of ions? So this is pretty easy because this is acetic acid, which is a weak acid. This is a base. Bases aren't going to give that. This is a weak base. This is a weak base, and this is a strong acid. So this is going to have the highest concentration because it's going to completely 100% ionize.